After years of cutting metal with an angle grinder and a handheld plasma cutter, I came up with this crazy idea to build my own CNC plasma table. If you ever considered building one yourself, or you just like watching other people do hard things, then you came to the right place. I'm going to go through my entire build from start to finish. I will detail my successes and my failures, so you can skip my errors and focus on your own. I built this table about 9 years ago, and I'm finally getting around to gathering all the photos to make this video. I didn't want to wait any longer in fear of being accused of procrastination. Well, better late than never. You know, for plasma cutters, that is. Maybe not so much if this video was about root canals. Creating a CNC plasma involves a few steps. It requires a combination of mechanical, electrical, and computer skills. However, this pales in comparison to the skill required to convince your significant other that this purchase is a good idea. Since I built this machine, some inexpensive options for turnkey plasma tables have come to the market. When I initially took on this project, budget-friendly, ready-to-run options were pretty limited, and I was able to save about $10,000 over buying a completed unit. I'm not going to encourage you or discourage you from building your own CNC plasma table, but only to tell you that there are more options if you want to skip the build process than there used to be. It is also a lot easier to hide a bunch of small parts delivered from a UPS truck from your husband or wife than a 10-foot long plasma table that comes out of a semi-truck. This is definitely a factor to consider for those people who are still working on that persuasion skill that I mentioned earlier. One major advantage that still exists for building your own machine is that you get the opportunity to really understand how all the parts on it work, and you'll be much better equipped if you ever have to make repairs. While you may not be able to save as much money as you could before, by building your own machine, you will still be far ahead when it comes to maintaining it. However, if you're feeling lonely, calling tech support might be a good option. Even if you decide to build your own machine, this video will give you a much better understanding of the fundamentals of a CNC plasma cutter table. If you decide not to build your own, you can just kick back, relax, and know that you don't have to do the heavy lifting. First, I had to decide how large a table to build. For me, it really came down to how much space I had. The only place I had to put this machine was underneath two back-to-back 12-foot wide pallet racks. I measured it out, and a 4-foot by 8-foot plasma table would be about the best I could fit. It would be about 10 feet long by the time I was done, and this gave me just enough room to maneuver on each end. This worked, but I would refer to the setup more as cozy than spacious. I decided from the beginning that this plasma cutter was going to have a water table. For those of you who are not aware, a water table is not the awkward uncle of the waterbed family. A water table is a large tray that holds the sheet metal being cut, and it's filled with water up to the bottom or slightly beneath the workpiece being cut. There are several advantages to using a water table. First, the most often noted benefit is the reduction in smoke. If the water level is close to touching the metal or touching it, you can reduce the smoke by at least 90%. Some people who use a water table do not use any fume control at all. However, I would still recommend some smoke extraction, even if it is minimal. Another huge benefit is that the metal stays cool to the touch. This is especially important in thinner sheet metal, which will easily warp. If the metal warps, the cut can become inaccurate, and in some cases, it can even cause the torch to collide with the metal. If you're cutting a very small piece of sheet metal, the torch colliding with it can actually move the workpiece on the table and create scrap. Also, you may have to flatten the workpiece afterwards if it warped during cutting. A part on a water table typically has less slag than a dry cut part also. Finally, in my experience, the plasma cutter just works a lot better with a water table. When I cut a part dry, I find that there's a lot more slag that builds up on the plasma cutter, and this causes a lot more faults and misfires in the machine. This requires restarting the cutting process by hand. Overall, the cutting process is much cleaner with the water table. As everything stays a bit cooler, the consumables also seem to last a little longer. The actual water table that holds the metal is 8 feet 6 inches long by 4 feet 6 inches wide. Being slightly larger than the 4x8 sheet of metal that I plan to cut allows for a buffer so that the plasma cutter does not work all the way to the end of the tub. If I did not make the tub oversized, I would risk cutting into the sides of the tub, and that would let the water leak out. Also, the overall movement of the head of the plasma cutter is about an inch more than the 4x8 foot dimension to provide just a slight fudge factor when trying to work close to the edge of a full sheet of metal. For my build, and I think most DIY plasma projects, it's pretty common to buy a gantry kit that gives you all the parts to build your Y and Z axis on the machine. These kits are nice because everything is worked out as far as the motion of the machine is concerned. However, you can still save a lot of money by acquiring the bulk metal to make the table locally. In my case, the gantry provider included the details on how to build the rest of the machine. However, I made some additional modifications to increase the capabilities for my needs. After ordering the gantry kit, I designed the table in SolidWorks using the provided specifications as a starting point. I ordered an extra wide gantry so that the cutting head could extend beyond the table so that it could add a rotary axis for cutting tubing and other round objects. This addition is still on the to-do list. Here you can see the table I designed in SolidWorks. On the right side, there's a large open area to put a 100-gallon water tank that'll hold water for the table. The water from the table empties into the tank to allow the table to be cleaned out and to have a place to store the water so it doesn't evaporate if the machine will not be used for a while. For clarification, I will be calling the axis in the long direction of the table the x-axis, and I will be calling the axis along the gantry, or the short side, the y-axis, because this is how my software is set up. On the left side of the machine, I have added compartments to store scrap metal for easy access and organization. This image shows the beginning of one side of the table. The main frame is made from 3-inch by 3-inch box steel with a 1/8 wall. C-channel is attached to the bottom of the post. Holes are put into the C-channel to allow a place to bolt it to the floor. All parts were held straight by clamping them in corner vices. This saves a lot of time over using squares or measuring corner to corner to calculate squareness. Because my floor is not perfectly flat, some of the feet were shimmed when the sides were stood up. A laser was used to get everything level. As we get further into the build, there will be opportunities to make slight adjustments to keep everything plumb, level, and square. However, the more accurate we can have things now, the better off we'll be when we get to those later steps. Anything that is off at this stage will just compound later on. As they say, an ounce of prevention is worth a pound of cure. And a pound of cure is worth a pound of flesh is what you get to keep now that you no longer have to cut things out with an angle grinder. You can see the laser here with the red line across the bottom of the box steel frame. Using a laser is helpful to build the welded assembly that is too large to put on a welding table. You could even build this outside in the dirt and keep it level just by shimming it up to the laser. Once everything was dialed in with the laser, all 4 corners were aligned and clamped together with corner vices. You can see how these corner clamps leave an open area for the welder to access. The locations that are accessible are welded with some short beads. After the clamps were removed, the other edges were finished up. I had to be careful to move around the structure when welding, so not to overheat any given area and risk pulling the frame out of alignment. The silver welding clamp is holding a board in place that makes sure the box tubing stays level. With some cross members in place, it is now time to add some 2-inch by 2-inch box steel risers that will hold the 4.5-inch steel plate that will act as a guide rail in a later step. I've added a fair number of clamps to make sure nothing shifts while I tack weld everything in place. The steel plates were added to the back side of the riser temporarily to ensure alignment. I used the laser again to check the alignment of the risers. If anything is off at this point, it can be adjusted. Everything is checked and shimmed and ready to weld. Scrap paper works great for shims because it's easy to fine-tune with the thin pieces. However, be careful not to catch it on fire when you're welding. Unless that's what you're going for, then just make sure you keep a fire extinguisher around. Here are some additional views of the shimming process. The risers are now tacked in place. I went over all the tacks with a 1-inch long bead every 6 inches. This is sufficient to hold everything together. Doing additional welds would not add any significant strength to the overall structure and would increase the possibility of warping. Plates have been welded to both ends of the tubes. These plates will act as stops for the stepper motors. This machine will not have limit switch stops on it. To square the gantry in the X direction, I will simply run the stepper motors until they hit the steel plates, and this will bring the gantries into square. The stepper motors will just misstep when they can't move any further. When both the front and back X-axis steppers are slipping, then I know it's aligned. The steppers skip for less than a second, and this does not in any way hurt them. Because these end plates are used to align the machine, it is extra critical that they are properly located and the box tubing they're attached to is square to the machine. If these plates are not perfectly located, it can cause the gantry to rack and become misaligned. Running the machine in this misaligned state can lead to inaccurate parts and possibly damaging the gantry. I've never found any benefit to adding limit switches to any of the axes. This would just be more electronics to fail and more setup in the controller. Before each cut, the machine has to be zeroed out to the metal being cut anyways. However, if you're dead set on making more work for yourself, go for it. Now that I have the frame done, I'm going to start building the tub that will act as the water table. This tray will hold about 100 gallons of water, and that's about 12,800 Jello shots if you're keeping track. The main structure of the tub frame is made from 3-inch by 5-inch angle iron that's a 1/4 inch thick. The bottom of the tray is made from a piece of 16 gauge 4-foot by 8-foot hot rolled steel. The entire perimeter is welded because this will need to be watertight. The next step will be to build a structure that'll hold the slats in place. The slats will hold the metal just above the water in the tray as it's being cut. Here is a photo of what it will look like done. On each long side, a piece of 2-inch by 3-inch by 1/8 wall box steel is welded in place. These pieces will act as risers for the slats that'll run across the table to hold the piece of metal being cut. Because the ends of the tube are sitting on the angle iron, the center section had to be shimmed up before welding to the sheet metal base. The slats are going to be spaced about 3 inches apart. The spacers are made from 2-inch angle iron welded to the side of the larger angle iron that makes up the walls of the tub. I made a fixture that provides for 3/16 inch spacing between the angle iron supports. The slats will be an 1/8 inch thick, which leaves just enough space to make them easy to install and replace if needed. You can see how the spacer works here. Because of the spacer fixture, I did not need to clamp any of the 3-inch angle iron pieces in place. I just held them by hand and tack welded them. Here we can see the table with all the slat supports installed. A piece of 2-inch by 3-inch box steel was added to the center to provide additional support for the slat. You can also see underneath the table, I have added some additional uprights. These do not provide any support for the table, but instead provide additional storage for metal. A piece of C-channel is welded to the side of the table to provide a place for the control cables. A plastic cable carrier festoon will sit in the track, holding the wiring for the CNC motors, the plasma torch cables, the air lines, and the plasma controls. A 1/4 inch spacer was added underneath the center of the box steel to fill in the space and keep it at the height that are the same as the ends that are supported by the angle iron. Here we can see everything welded in place from one end. 4 welds were done on each angle iron spacer. There will not be much force on them, so that's all that's required. Here's another view from the far end. You can see the 1-inch pipe welded to the end. This will be the water inlet fill for the table. On some builds, a pipe just goes over the top lip of the tub, but this can be in the way when the machine is in operation. A 1-inch bulkhead fitting has been welded into the floor of the tub. This will act as the drain. Everything was painted with a gallon of Rust-Oleum paint to reduce rusting. The perimeter weld bead that holds the piece of sheet metal that makes up the floor received an extra heavy layer of paint to seal any pinholes and make it watertight. I was concerned that this may not last, but it has never leaked. Even though all the paint has come off the floor of the tub, it is still sealing up the pinholes. Also, if needed, I can just recoat it. After the paint dried, the 1/8 inch by 3-inch wide steel strips were put in place. These strips will hold the workpiece as it is cut. The strips of steel are installed using a wavy pattern to help better support the sheets of metal. This keeps the metal from tipping when the torch pushes on the corner to zero out the torch height. After the frame is completed, I then added plywood shelves for metal storage. The larger section can handle up to a 3-foot by 4-foot sheet, and the smaller compartments can handle about 16 inches tall by 4 feet wide. This is very handy for me because most of my work is prototype in nature, so I will typically just make a few small parts at a time. Or if you're just into hoarding, this can make you appear really organized. Next, I will install the 4-inch wide by 1/2 inch thick steel flat bar that'll act as the track along the long axis. Earlier, I drilled mounting holes in the bar stock with my mill to attach this to the 2-inch by 2-inch riser that I welded in place in the earlier step. I used a bunch of clamps to hold everything in place to make sure that nothing moves before I can get the holes marked. Here you can see an additional clamp that I used to space the track 1/2 inch in from the frame. To mark the riser, I use a transfer punch that just barely fits in the drilled hole. Transfer punches come in kits that are sized in 1/64 increments, just like drill bits. These punches have a very small point, and if you use the largest punch that'll fit in the hole, it'll accurately mark the center point of where I need to drill and tap the mounting holes. With a hammer, I mark where each hole center will need to be drilled. After center punching all the holes, I removed the 4-inch by 1/2 inch plate steel. With the holes marked, I was then able to drill and tap them with a 3A16 thread. As mentioned before, With this table build, I chose to purchase a Gantry kit. This kit was produced by Precision Plasma. I do not believe they are still in business. Overall, it has worked well and was reasonably priced. Unless you are working from a design or have a detailed plan in mind, I would highly recommend purchasing a Gantry kit that has all the bugs worked out and includes all the parts. Trying to find all the small parts that you'll need to complete the design can become very time-consuming and expensive. This gantry is made from 2080 aluminum T extrusion. I purchased the extra heavy-duty kit because I wanted to also be able to mount a CNC router to the gantry to do CNC milling. If I was to build this myself, I probably would have used box steel tubing because I would know everything was welded together rigidly. However, this aluminum is very heavy duty and it's easy to mount all the various components to it. Overall, it worked out well. Up top, you can see the cable management carrier. Below is the main extrusion that makes up the gantry. At the bottom is the gear rack that'll mount under the 4-inch by 1/2-inch steel box track and also be used for the Y-axis gantry. Here you can see the risers and the base for the gantry. The kit comes with all the fasteners, pulleys, belts, and a bunch of CNC machined parts. The flange bearings support the timing belt pulley. Thankfully, all the parts came in labeled bags. You can see the CAD drawing that was included to help with the assembly. Everything was nicely wrapped up and came well packaged. Pulleys provide gear reduction for the stepper motors, which increase the torque. Most of the details, down to the Loctite, were included. Here, you can see the Hypertherm Power Max 65 plasma cutter that'll run the table, and the 3¼ horsepower Porter cable router for the spindle. Here is a view of the linear track assembly fastened in place. This is the aluminum extrusion that makes up the gantry. As mentioned before, I purchased the extra long extrusion for this machine that'll hang off the end of the table. With everything unwrapped, you can see the Z-axis and all the laser cut plates that'll make up the drive assemblies. These all came powder coated and ready to assemble. This is the plasma torch bracket, which is designed to hold the long style machine torch and the bracket to hold the router. Next, I need to install the X-axis rack gear that'll provide the motion in the long direction. Racks are flat gears that provide linear motion. I don't know exactly why they call them racks, but I think it has something to do with this. Because this rack needs to be about 9 feet long, and it was shipped in 2 4-foot 6-inch pieces, I need to weld them together to get to my required length. The kit came with a short piece of rack to use as a welding fixture to space the pieces apart as they're welded. I ground the ends of the rack to provide for better welding penetration. To keep everything straight, I bolted the pieces of the rack to a piece of angle iron. Here I've tack welded one side of the rack. I have to remove it from the clamps to weld the other sides. I've reclamped the rack back onto the angle iron to weld the other sides. The rack is held in place with 3M super strength molding tape. First, I apply the tape to the back side of the rack. This tape is extremely strong, but both surfaces have to be very clean, and it does take a little while for the tape to reach maximum strength. I cleaned off everything with acetone and then clamped it in place using a piece of wood to distribute the load across the entire length. I had to repeat this procedure on the other side of the table. I left the clamps on for about an hour to make sure that the adhesive on the tape had time to fully bond. Because of the large surface area, the bond on the rack is actually very strong. The foam in the tape also provides a slight bit of cushioning to the system. It has been 9 years and everything is still holding in place just fine. There is a lot of debate about the accuracy of a system that uses standard steel plate for tracks and ball bearings for guides. In more recent years, the market has been flooded with linear ball rails, ball screws, and all types of bearing tracks and assembly. Many people will balk at using a design like I have on my machine, stating that it will be very inaccurate and not make good parts. While there could be some merit to the increased accuracy you can get from using linear rails and ball screws for providing the motion, it may just not be as justified as it appears. Standard plasma cutters just aren't as accurate as a lot of other tools like a CNC laser or CNC mill. The benefits you would gain from linear rails may not even be noticeable when you compare it to a properly aligned and adjusted steel plate track like I have on my machine. Keep in mind that the low-cost linear rails that are now on the market are made from low-quality import ball bearings that just won't have the longevity of the higher end units. My simple design here may actually last a lot longer. Chasing accuracy on a plasma cutter may just be a solution without a problem. If you plan to also use this machine for any type of precision routing, I would definitely look at upgrading the rail system. However, if you're purely using the machine as a plasma cutter, your money might be better spent elsewhere. This design is simple, durable, and it's performed well. The one downfall is that the flat bar will accumulate splatter and dirt and will need to be swept off on a regular basis. However, this design does not require any special shielding or baffles or complex structures within the gantry to keep the linear rails in a protected location. I'm sure there are many viewers who will disagree with me, and given the current market, there is some justification to using a more precision linear motion system. When I built this machine, there were not any reasonably priced linear rails on the market. Also, given the size of the machine, even the cheap imports that'll properly handle this weight are not going to be inexpensive. Saying that, if I was to build this machine again, with what's available today, I would consider linear rails, but more so because I have a router mounted to my gantry. This router is more capable of taking advantage of the higher accuracy. However, this adds a whole new level of design consideration to the machine. There are also limits to router cutting parts on top of a table that is designed from metal slats meant to support steel. This surface is not very flat or accurate, and will become less accurate over time as the plasma cutter slowly degrades the slats. Plasma cutters are designed to adjust the cutting height to accommodate for this. CNC routers are not. Being this is not a very accurate or stable surface for router cut parts, it is really not suitable for any three-dimensional profiling. So now we're back to looking at how this table would have to be modified to work properly for a router. This brings me back full circle to the idea that I would probably only use it as a router table to cut out basic two-dimensional shapes. This would be mostly from plywood or other sheet stock for non-critical applications. Considering the limitations of the bed of the machine, I still believe my design is completely sufficient. So now that I have my viewers more divided than Ford versus Chevy, Democrats versus Republican, Star Wars versus Star Trek, let's take a look at the y-axis, which I am sure some of you would like to convince me is actually the x-axis. To throw another wrench in the wood chipper, this axis uses a different linear motion system with V-groove bearings. I may need to make an entirely separate YouTube channel and call it the Haters Club, where we can just all sit around and bitch about the good old days when we didn't have all these choices but somehow had to get everything done. Also, make sure you stick around to the end when I cover the real controversial issues. In this photo, you can see the y-axis. This is made from an aluminum extrusion and it's attached to the main gantry with T-nuts. I had to do a little calculation to figure out exactly where to place the y-axis extrusion on the main gantry beam because this extrusion is shorter and has to be placed according to the limits of the machine travel. It is capped with steel to increase the wear resistance because V-groove ball bearings will ride on it. Here I am checking the spacing on the opposite end just as a double check. I'm installing and spacing all the T-nuts, getting ready to bolt everything together. After bolting these two parts together every few inches, it essentially becomes one piece structurally, which adds to the overall rigidity of the gantry. Similar to the x-axis, I have to add a gear rack to the y-axis. I have the tape installed and ready to attach. You can also see the galvanized steel tray that'll be used to hold the wire routing for this axis. Like before, I have installed the rack on this axis and clamped it in place with several clamps and a wood strip. You can see the large washer that I temporarily installed on the T-slot to properly align the track with the top of the extrusion. Next, I need to assemble the uprights that hold the y-axis above the table. I ordered these uprights to be a few inches taller than would normally be used for a plasma cutting machine. This raises the z-axis. I also had to order z-axis assembly with more than the typical z-axis travel. That way I would have more options when using a router. If I had gone with the standard gantry, I would have been pretty limited on how thick of workpiece I could have put under the router. When using a router, I need to place supports above the slat table to provide a level surface, and I also need a spoil board on top of that so the router has something to cut into as it's cutting through the parts. This will raise everything several inches. After aligning and assembling the uprights, it was time to put the plastic caps on the ends. These push-in fasteners held everything together nicely and provided a nice aesthetic detail. Before I put the caps on, I installed a bunch of T-nuts in the slots, which will be used to bolt on the frames of the drive mechanisms that will house the gear reduction pulleys and support the pinion gears that ride in the gear racks that I already installed. Here I installed the bearings that will lock the gantry's linear motion to the 4-inch wide steel plate track. I'm using some machining parallels to get everything square and properly spaced before I lock down the fasteners. These bearings will hold the weight of the gantry and prevent it from moving side to side. There was a small amount of slop in the mounting holes, which allowed me to get everything aligned before cranking it down. All of these fasteners have thread lock on them, so they won't move once they're in place. Here you can see I'm using the machine parallels to space the bearings exactly 1/4 of an inch up. By doing this on all the bearings, I was able to keep everything level. Because when you crank on the fasteners, it'll want to move slightly. I had to get everything snug and then tap it into place for final tightening. I use the same process for the guide bearings to get them equally spaced. Here I need one shim to space them out 1/8 of an inch. On the other side, I used an extra shim to space them out 1/4 inch. To make things easier, I clamped all the parallels in place so I could focus on aligning and tightening the bearings. The assembly is in place and sitting on the steel rail. Here's the drawing that was provided by Precision Plasma. You can see how I ordered an extra wide gantry where one end hangs past the end of the table. I'm using a laser level to make sure my X and Y axes are properly aligned. The lasers are accurately tracking, so now I can tighten any final fasteners on the end of the Y axis track. A rubber stop was included to prevent the Z axis assembly from coming off the track. I will say that the stop should have been a little heavier because I did push it off the end with a stepper motor. This drawing shows a standard assembly for the gantry uprights. You may notice in this design print that the gantry does not have the additional height that my setup has. With everything aligned and in place, I slightly loosened the inboard bearings to align the gantry to the track. There was a tiny amount of slop that allowed the entire gantry assembly to move side to side. After loosening this, I was able to move it in about 30,000th of an inch to get everything nice and tight. Now that the gantry is in place, it is time to add the flange bearings, pinion gears, and the pulley to the assembly. These plates were assembled off the machine without the fasteners tightened down so they could be adjusted later. At this point in our adventure, it's extremely important to know that the word pinion comes from the Latin word pinna, meaning both feather and battlement. I'm starting to see a theme here. Next, the speed reduction pulleys were installed and the outer plate was added. I used a square to make sure that everything was aligned before it was bolted together. Next, the gear reduction assembly was attached to the gantry on both sides of the machine to provide the X-axis motion. This machine will have one motor on each side so that the Y-axis does not get racked or out of alignment when moving. Here I will assemble the drive mechanism for the Y-axis. You can see that the Z-axis, which is sitting on the table, is installed to the plate before it's attached to the machine. You can also see the V-groove bearings that will provide for the linear motion in the Y-axis. The gear coming out of the pillow block will ride on the Y-axis rack. From this angle, you can see the gear reduction in the Y-axis. This is basically the same as the X-axis, except it only needs one motor and one gear reduction. The stepper motor is attached to the speed reduction assembly. Because plasma cutters do not need to move at high speeds, this gear reduction significantly increases the power of the table while increasing the accuracy by increasing the number of steps the motor moves per revolution of the pinion gear. Here the Y-axis is installed on the track with the V-groove bearings. The Z-axis assembly is also in place. From this view, you can see how the rack and pinion system creates the Y-axis motion. After I first assembled the gears, they did not quite align properly, so I had to take them apart and realign them. I installed the limit switch that will trigger when the plasma cutter torch makes contact with the piece of metal that it was cutting. There is about 100,000th of an inch of travel in this assembly, and this is programmed into the software so it knows to lift the torch an extra 100,000ths after triggering it. This is because it'll drop back down after it is lifted. This will provide a proper offset distance from the metal being cut before the torch fires. The wire routing carrier is attached to the channel. This is the one area of the design I was not completely happy with. I was afraid that these protruding fasteners could potentially cut into the wiring that was in the track. Here I modified the design, I countersank the holes in the plastic carrier and installed some flathead bolts. On the end of the channel, I also was not happy with the sharp edge, so I smoothed it over and added some rubber tape for additional protection for the wiring that would be sitting there. From another angle, we can see the carrier in place and ready to install the wiring. I have the Z-axis motor installed, and you can see a heavy gauge extension cord which has been added so that I have a place to plug in the router when it is in use. The drill is temporarily attached to the end of the motor so that I can move the Z-axis manually. I am going to install a mister on the Z-axis so I can use it when I'm router cutting aluminum. Here you can see the wires installed. The large wire is the main plasma lead, and the white tubes are for the misting system, air and liquid coolant. The black lines provide air power for the Z-axis motion of the pneumatic engraver that I'm also installing. The plasma torch is routed, and you can see where the X and Y axis intersect. It's getting a little crowded here, but the mister is in place with the plasma cutter mount partially installed. Here is a close-up of the mister assembly. I had to tap into the Z-axis block to provide a mounting point for the misting system hoses. This is a very cheap import mister that does not have good control of the coolant flow. I was going to replace this with a better unit, but the plasma cutter does a really good job cutting aluminum, so I do not see myself using this machine to cut aluminum with a router. Because of this, I just removed it. This is the air dryer and oiler for the engraver, also along with the air solenoid for the misting system and the pneumatic plate engraver. There is a third air solenoid to move the Z-axis for the engraver pen. The engraver just needs a simple up and down motion, but I need to be able to vary the pressure that it puts on the plate that it's engraving. Because of this, I can't use the Z-axis stepper motor to plunge the engraver into the metal. Finally, this is the relay to turn the router on and off. Here is the Z-axis I picked up off eBay that I will mount the engraver pen to. This is a pneumatic linear air assembly. Air pressure will move it up and down, and adjusting the pressure will determine how much force the engraver pen pushes into the workpiece. Because the axis is powered by a pneumatic cylinder, the pressure on the plate will stay fairly consistent even with small changes in material height. To get started, I machined some scrap aluminum to get square edges. Here I have my blocks of metal squared up and ready to be machined into their final shape. Next, I will need to make a clamping plate that'll hold the engraver in place. I have placed a piece of wood between the aluminum plates to space them apart during machining, allowing for an adjustable clamping force on the engraver. Using a center drill, I started a pilot hole between the two plates. The larger drill bit will be used to make the final hole size. Here's a close-up of the plates ready to drill. The mounting blocks now have the final hole size. You can see how the wood spacer, now removed, created a proper gap to hold the engraving pen. I've added the bolts to the assembly, which now hold the engraving pen in place and attach the mounting blocks to the pneumatic Z-axis. Here's another view from the top side. From this view, you can see the top air fitting and the attached cylinder that'll push the pen down into the part being engraved. I've now reassembled the bottom part of the pneumatic axis back into the assembly. The Z-axis includes stops that allow you to adjust how far it can travel in each direction. You can see the Z-axis moved into the down position. On the back side of the Z linear slide, I added an additional mounting block so that I can attach it to the Y-axis of the machine. Two spots are center punched where I need to drill a hole so that I can mount the block I just made. Here you can see the holes drilled. I put a piece of scrap metal between the mounting plate and the track so I did not drill into it. I have the engraver assembly loosely attached to the Y-axis plate, and I have shimmed it out to keep it straight. With the bolts tight and the shims removed, it is now time to lock it in place. From the side, you can see how it's all bolted together. Fully assembled, plumbed, and ready to go. Because of space constraints, this assembly had to be mounted sideways. Because my plasma cutter mount is magnetic, I created this extra black housing to add to the assembly. This provides a mounting place for additional electronics and also provides a place to put the plasma torch out of the way when the router is being used. Looking at the backside, this is where additional controls will later be mounted. It took a while to get all the tubes and wiring straightened out with just the right amount of extra loop to allow for proper movement of the mechanical parts. You can see how I had to notch out the custom bracket to fit around the flange bearing. This Feather Touch ohmic sensor was an optional add-on. This feature allows the torch to know when it has touched the metal that it is cutting by completing an electrical circuit between the tip of the torch and the metal being cut. Without this feature, the torch has to push down on the metal until the torch is lifted up and hits a limit switch. This can be a problem with thinner metal as it may just bend instead of lifting the torch. While this is a nice feature for cutting thin metal, I found it to be more problematic than it was worth. If your metal has any rust on it or other surface dirt, oil, or paint, it may not complete the circuit. Also, if there is slag or anything build up on the tip of the plasma cutter, you may have a similar problem. Additionally, when using a water table, which I find extremely important when cutting thin metal to prevent warpage, it causes additional problems with the electrical circuit. I no longer have this installed on my machine. Here's a close-up view of the festoon wire carrier. The Feather Touch sensor is installed on the custom bracket. This is the plumbing for the table system to empty the table water into the tank below the table. I added a spin-down filter that I was hoping would catch debris coming from the table instead of depositing it in the water tank under the table. If I did it again, I would go with something else because it quickly clogged up. Some type of baffle system that would catch the debris would be much more practical. This large PVC ball valve is used to empty the water table. The chrome-plated float switch was intended to turn the water pump on and off as it filled the water table from the tank. I found this to be fairly unreliable, and it was way easier to just manually monitor the water level and shut off the switch when it was full. So much water would evaporate from the table that I was usually topping it off with a garden hose anyways. This is the relay that I used to turn the water pump on and off from the float switch. This is the float switch assembly that I made that was put next to the water table at the same height to monitor the water table level. The idea was that the capsule could move up and down in the bracket to vary the water fill level. A tube attached to the bottom of it and to the water table was used to keep the water level the same in each. Even with a sufficiently sized breather hole in the top of the capsule, it did not really work very well. This is the switch box that housed the relay for the water pump. Here's the pump float switch with the relay installed. You can see the water level tube installed between the capsule and the table. This is the pump I used to fill the table from the tank beneath it. It's an old pump I had lying around, but they pretty much last forever. Here you can see the pump filling the water table from the tank below. I added a one-way valve to the plumbing so that the water doesn't go back into the tank once the pump is turned off. Now it's time to bolt the table to the floor, but my floor isn't very level, so there will be a fair amount of shimming. I use a crowbar to gently lift the feet and place the shims underneath it. Here are a bunch of squares I cut out of thin aluminum to use as shims. A box of concrete screws are used to attach the table to the floor. The table does not shake around much, so it didn't need any heavy anchors. I had a bunch of thick thumb nuts that I used as washers. Here you can see it bolted to the floor. There's a lot of debate about how to properly ground the plasma cutter. I ended up running the workpiece ground from the cutter to the table and then I attached the ground clamp wire to the same lug and then ran that to the ground rod in the floor. This seems to work pretty well. The control system I purchased for this machine was called EtherCut, and it came from CNC. I purchased this setup because it could easily run a CNC router in addition to a plasma cutter. This system ran on Mach 3 software. Mach 3 was never designed to run a plasma cutter, so it took a lot of modification, or maybe more accurately described as hacking, by CNC to make it work. This setup was very complicated to get the machine to run. Even worse, Newfangled Solutions, the maker of Mach 3 machine control software, was in the process of dropping support for it even back then. 10 years after dropping support for it, it is still used quite a bit for CNC machining, but I don't think anyone really still uses it for plasma cutting, except for people who set up the system a long time ago and don't want to upgrade. CNC has since switched to a Linux-based system. I don't know much about it. I really wanted to like this Mach 3 system because of its versatility, but it had problems from day one. The feather cut system used for cutting thin sheet metal was dead on arrival and had to be replaced. Also, the entire system would glitch out and skip steps on the stepper motor. The machine constantly made bad parts. After spending about a month on the forum being told I did not know what I was doing, I put everything aside for about a year because I had hit a dead end. After that, I needed to get the machine working because the projects in my shop were stacking up. After much fighting back and forth, I finally sent the whole controller assembly back to them, asked them to put it on a bench test, and I would pay for the diagnosis. It turned out that the system came with a bad stepper driver. They did fix it for free, but by then I was completely over it. At this point, I contacted Precision Plasma, who made my Gantry, and the owner suggested that I look at a system made by Spark Robotic. I ended up replacing the whole setup with one of their units and have not had any issues since. What I purchased from them was essentially a repackaged plug-and-play controller made by My Plasma CNC. The system was very simple and unfortunately did not have any support for a CNC router. However, I was just happy to have it working at this point. To use it, you pretty much just drop a DXF file into the software, make a few adjustments, and hit cut. I wish the system had a few more features because there's a lot of manual fine-tuning before you start cutting. However, the software is free and it does work. It's a good option if you're not doing a lot of complicated parts and you don't want to learn complicated software. More recently, My Plasma CNC has made some software updates that include some very basic milling features that allow you to run a CNC router. It lets you do multiple passes over a sheet at multiple depths. This should be sufficient to cut out plywood, foam, sheets of plastic, or even aluminum. Also, I expect this mode to work for my engraver mounted to the Z-axis, and it should work for a drag knife too if I ever decide to go in that direction. When I get some more time, I will work on adding these features to the table. I think this will really add some good useful functionality to it. One day, I would like to get a large, dedicated CNC router, but this will just have to do for now. Along with the software and the control system update, I also had to change the torch mount because it used different type of sensors. This torch mount is not magnetic like the original one, so I will have to unbolt it if I want to put a router in its place. Because a router was not an option when I purchased the new control system, I sold off the router and the mounting bracket that came with the original Gantry. If I do reinstall a router, I will probably use a 4 kilowatt air-cooled spindle instead. If I was doing a permanent installation, I would use a water-cooled unit, but it's more than I want to deal with on something that's going to be used very occasionally. We can take a look at how the metal is being stored on the racks for quick access. I also have some plastic stored here, which I use on my laser cutter, but we will look at that in a different video. This here is the water tank that stores the water for the table. You can also see the pump that is used to move the water from the tank to the table. This is the grounding rod that ties everything together. Because this plasma cutter uses a blowback ignition system for the torch, one grounding rod is sufficient. I have another video dedicated just to the details of the ignition system, which is crucial to understand if you're going to be building or using a CNC plasma table. You can see how the steel bar tracks connect debris over time. I thought this was going to be a big issue when I initially built the machine, but it's not so much if you just wipe it off occasionally. I've installed some fans with filters to pull the smoke out of the machine. Because the smoke is being blown outside, technically I don't need the filters, but I put them on there because I wanted to keep stuff from building up on the fans. Placing the cutter directly under pellet racks allowed for a good place to mount the lights. This makes it really easy to see what I'm doing. This is the software interface that I'm currently using. Using the manual control buttons, I can move the plasma head around to locate it where I need it to start the plasma cut. If I lower the torch head into the metal plate, it'll stop as soon as the torch lifts up and the magnetic sensor will sense an open circuit. Here I am demonstrating how the plasma head can move along the Y-axis off the end of the machine. This is where I will install the rotary axis. Another useful feature of being able to work beyond the area of the table is if you want to cut something that is too tall to fit on the table. One example I can think of is if you had to cut out holes in a large metal box. I could place the box next to the table and cut it out without any problems. I can officially say I did not do this project because it was easy. I did it because I thought it was going to be easy. And with hindsight being 20/20, or at least slightly less blurry than when I took on the endeavor, I can say that spending the money on a good gantry kit was key, and finding a control system with user-friendly software can make a real difference. Luckily, there are more available options on the software side than there were when I built my machine. I have not researched all the choices, but I'm sure a little research on your part will help you figure out what people are happy with and what they aren't. Another thing I would like to mention is my choice of motors on this table. I'm sure some of you out there are cringing this entire time because I did not use servo motors and you don't believe any legitimate machine should ever use stepper motors. I can say over all the years, I've never had a skip step without the gantry physically running into something that shouldn't have been there. There was the one exception when I did have a bad stepper drive. These stepper motors provide far more power than is needed for any normal operation. In addition, their operation and the setup is very simple and costs way less than a servo system. I do not see any justification to using a servo drive system on a DIY or low-cost industrial machine. I want to take a moment to discuss one of the most overlooked aspects of purchasing or building a CNC plasma table. We take all the time looking at the machine specs and figuring out which features we need and trying to make it work in our budget. However, if you're considering purchasing a CNC plasma cutter, one thing you really need to think about is how you're going to load the metal on the table. Even if you will be loading it by hand, make sure the table is located somewhere that'll be easy to get the sheet stock to. In my old shop, I only had one large garage door, so I could not block it with the plasma cutter. That meant that I had to maneuver materials through the shop to load the machine. I had a forklift, but my welding area was between the plasma table and the door. This meant that the path to get to the table was usually not open to the forklift. No one wants to have to rearrange their shop to load the table. Since then, I've moved to a new location that has several large roll-up doors. I placed the machine right in front of one of the doors and placed the sheet stock on the pellet racks above it. Now I have access to the materials from the outside and can load the machine without even going into the shop. This is a real game changer. Ultimately, we all need to work with the facility we have available to us. If you are considering bringing a large piece of equipment into the shop with significant material handling needs, it is worth the time to reevaluate your shop layout. Here's a video of the plasma table cutting out some wood with the router before I switched over to the new computer system. This is 3/4 inch plywood that I cut out to make a large pit couch. Here are some decorative panels I'm cutting out of aluminum with the new control system. I put together another video explaining in detail how the ignition system works on the plasma cutters. It is important to understand this process if you plan to build or buy a CNC plasma table because the technology has changed a lot over the years, and using the wrong type of plasma cutter on your table can be disastrous.